Okay, I hope I'm audible to all. Okay, so let's just start. So a very good evening all. And uh, today I'm going to take a problem solving course on uh, on the course Coordination Chemistry, which is taken by Professor Devasis Ray. So myself Satyaprakash Yadav, a PMRF scholar from August 2020 batch. Um, I'm working closely with Professor Satish Patil in Solid State and Structure Chemistry Unit, Indian Institute of Science, Bangalore. So about the course, so this is the 12-week course. 12-week course. So in week one problem solving session, we have discussed the introduction to coordination compound, their definition and classification of ligand. There are basically three types of classification: ligand 1, 2, and 3. Then in week two, we have discussed detail in the nomenclature part. Uh, and there we have discussed neutral, cationic, and anionic, and we have the cationic, cation and anion both are complex. How we will write those things also we have discussed. In week three, we have basically discussed about the coordination numbers. What are the different kinds of coordination number available from 3 to 12, and what are their corresponding stereo, what is their geometry. And in week 4 we are going to discuss about the different kind of structural and stereoisomerism. So if you go to the class lectures. So in lecture 11, professor has discussed about the concept of isomerism and structural isomerism. And lecture number 12, he has discussed in detail the concept of cis-trans isomerism, facial and meridional isomerism, and stereoisomerism. And in lecture number 13, he had discussed about the different kind of coordination equilibria and what are the stepwise formation constant and what is the overall rate formation constant. So uh, before going to the like problem solving session, I will just briefly discuss about what professor has discussed. 1 minute. Okay. So yeah. So first, professor has discussed about the isomerism in the coordination compound. So there are two types of isomerism. One is the constitutional and the other is the stereoisomerism. Constitutional means structural isomerism. Here, atom connected to the coordination metal center is different. Here, there are different spatial arrangement of the ligand around the metal. So in this, the professor has discussed about two kinds of isomerism: coordination isomerism and leakage isomerism. So coordination of ligand and counter ionic. So if we go to the detail, what is the structural isomerism? So first is the coordination isomerism. So here we can see the different types of isomerism: structural isomerism and stereoisomerism. Structural isomerism, we have coordination isomerism and ligand leakage isomerism. And in the stereoisomerism, we have geometric and optical. So in geometric, we have cis trans. In optical, we have lambda and delta kind of. So dextro liberatory. So first of all, sorry. So so first of all, like what is coordination? So here what we have like uh, in coordination isomerism, basically isomerism which involve exchange of ligand between the coordination sphere, and the ionization sphere. So suppose we have CH3 NH3 5 SO4 Br. Now Br will exchange from the ionization sphere to coordination sphere, and subsequently SO4 will go to the uh, from the coordination sphere to ionization. So it's called coordination sphere, like isomerism. Now, ionization isomerism differ in that basically what is anions binded to the metal ion. So suppose we have this CuNH3 5Br SO3 violet in color. So we have CrBr1, but in other case we have like SO4. So Br minus is so CSO4 bond here and C for that kind of awesome. Linkage isomerism where a project where like ligand have two different so sites to bind to the metal center, like NO2 CN. So NO2 can bind through N center or O center, and similarly CN it can bind through N center or C center. SCN where it can bind through S center or C center, like that. So structural isomerism, like if I give some example, like suppose we have this. This is the again the coordination isomerism, like three isomers for CrCl3H2 like now water molecule will go inside and Cl will go outside. So first iso-violet, this is CrCH2Cl3. Now one water molecule is out, two water molecule are out. So there are three types of isomerism is possible. Linkage isomerism, where ligand has two types of bonding, like suppose it can bind through N center or it can bind through O center. So this kind of isomerism. Now in stereoisomerism, we have basically two types of. So geometrical isomerism. So geometrical isomerism cannot be found in 2, 3. It can't be found. Cannot be found. It can find only 4 and 6. Now, in 4 tetrahedral, it will not found because all the ligands are adjacent to each other. So we have only square planar coordination number 4, and we have octahedral coordination number 6. Now we will go in detail. So suppose for coordination number, sorry, okay. Okay. Yeah. So we have this diastereomer. So basically, they have, what is diastereomer? They are not superimposable to each other. Those are called diastereomer. So now we have cis. Cis means adjacent curve. Trans means they have across the curve. So now if we go for the like um, go for the first, suppose we take one by one. I will take MA4, MA3B. If these types are, this cis trans is not possible. Only MA2B2 is possible. Now there is two transons. So whether A like can be like this. This is called trans, or it can be like cis to each other. A B B. So this is the. Now we will go to the MA B C D. So there are three kind of isomers. Three kind of isomer can form. So you fix A. Now you vary all the three. So there are three possibles. Now we can go to the MA2BC. Again here M. Now whether A is in cis part or A is in the trans part. So through this we can decide whether it is cis or trans. Then we have this MAB2 type. So we can see that what is the possibility here. So they have A, B, A, B. So this is cis. Another one is like trans. We have A, B, A, B. So this is your trans and this is your cis. Okay. So this is all about the geometrical isomer in octahedral. So we can see that as here, whether it is cis So suppose this is I think Ma2B4. So where A is this in the trans condition, this 2 trans condition, and other is like trans condition, and here is the cis condition. So this is the cis, like adjacent to each other. This is the cis, 2 cis and 2 trans can be possible. Sorry. Yeah. Okay, then we have like octahedral concepts, like if we have M.
Hello, sir.
Yes, yes, I can hear you. Can you hear me?
Hello.
Yes, can you hear me?
Yeah, what about my queries
Yeah, yeah.
related with assignment number 3 and assignment number 4?
Okay, okay. 1 minute, I'm coming. I'm coming. It is okay. Let me go to the problem solving session directly then. Instead of teach me. So, have you written your like a query somewhere? Just tell me your
Uh,
question.
Assignment 4, the identification of isomerism for cobalt hexaaqua.
Okay. Anything else? After that, Cl2 something, Cl3. Hello. Hello. I can't hear you. You are muted. Hello. Hello, ma'am. Okay, so let me go further. So question number one. So how many structural uh, pos structure isomer sorry, structure isomer possible in CONH3 6Cl3? Ma'am, can you tell how many structure isomer possible for CONH3 6Cl3? How many structure possible? So how many structure possible for CuNH36Cl3? Okay, so let me tell you, this is the first water complex. So there are four possibilities. So it can be CO, NH3, 6, Cl3, that is the first, CO, NH3, 5, Cl, Cl2 dot NH3. It can be CO, NH3, 4, Cl2, Cl dot 2 NH3. It can be CO, NH3, 3, Cl3 dot 3 NH3. It can be one more possibility. Here two possibility. One will be the cis, another will be the trans. Okay. So how many isomer is possible for PT NH3 to Cl2? Okay. So let me see what is the possible. So this is PT NH3 to Cl2. So basically it's a Na2B2 type complex. Here it will be platinum. It will be NH3 NH3 Cl, that is one, platinum, NH3 NH3 Cl. So this is cis, this is trans. So there are two isomers possible for this. If a plate rotate to a right direction, then it would curve. So if it is rotating plane product towards the right, it is called dextrorotatory. If it is rotating left, then it is called levorotatory. Yes, ma'am. Hello. Yeah, fine. Okay, go to the next. High formation constant of a ligand substitution reaction means ligand substitution is less feasible, the rate of backward reaction is high enough, the rate of forward reaction is high enough, or reaction remain in the equilibrium. Can you tell me what is the answer for this question? So the correct answer is like rate is nothing but K concentration of like reactant by power their stoichiometry. So if rate high formation constant means your rate is directly proportional to the rate constant. So the rate of forward reaction is high enough. That's why high formation constant for like ligand substitution reaction. So go to the next question. CuNH3 5H2Cl will react with any Na2 and concentrate HCl to form a compound which exists in both yellow and red form. What is expected isomerism here? Can you tell me? Otherwise, I will just go and explain this. So the like CuNH3H2Cl react with NaNO2. So that we can see that if it is react with NaNO2, what it will form? It will form CuNH3 5NO2. Now we have this NO2. NO2 can bind through NO2 or ONO. So this is binding through N and here it is through O. So basically this is the ligand isomerism or linkage. Okay. Addition of Ki to a solution of AgNO3 to NO3 precipitate AgI, but no precipitate formed when Ki is added to the solution of KAgCN of same molar concentration as amine complex. If instability constant are two constant of K1 and K2, what is the correct relation? So this one is from the lecture number 3. So this is directly, as you know that first reaction is happening, second reaction is not happening. Means definitely your K1 is greater than K2. That's why K1 is favoring over that, but K2 is not. So this is the simple reaction. 6 is A. KFe2Cr3 Cn KCr3 plus FeCN6 will show. What kind of isomerism it will show? Coordination is sphere isomerism. Yeah, you are correct because this is the ion from outside and inside the um, basically coordination sphere where basically what is happening where interchange of ligand between uh, like uh, coordination sphere and ionization sphere. So basically coordination sphere and ionization sphere. So here iron is chromium is in the coordination sphere and iron is ionization sphere. Here chromium is in the ionization sphere and iron is in the coordination sphere. Yeah. Cr3 bonded thiocyanate is bonded by N of NCS because. Just let me know what is the answer for chromium 3 bonded with thiocyanate complex is N of NCS because chromium 3 is hard metal whereas N is soft. Chromium 2 is soft metal and N is the also soft. Chromium 3 is soft metal ion where N is hard. Chromium 3 is hard metal where N is the also hard. Okay, so this is called HSAB principle. So what is called hard, and soft. This is the concept will give the most stable acid or base or salt. This is called HSAB principle. Hard, soft, acid, base concept. So basically, if both are hard and hard, then that will be the stable, or both soft or soft. So basically, nitrogen is a hard element, and metal in higher oxidation state is also hard. And like sulfur, oxygen, they are soft. So here nitrogen is hard and Cr3 is also hard. That's why the option D is correct. Cr3 is hard metal and N is also hard. How a cis-trans isomerism can be chemically distinguished? Reacting with monodentate ligand, reacting with ambidentate ligand, reacting with a bidentate ligand. Our option D is no. Okay, let me show you. Now we have suppose PT Cl NH3 NH3. Again we have one trans. Suppose we have PT Cl NH3. Now, if we react with monodentate ligand, this will substitute, there is no effect. But if we react with a bidentate ligand, what will happen? This can easily react, but this will not. So, bidentate ligand can easily react with cis over the trans. So that's the, like, chemically you can distinguish how is a cis and trans isomer can be chemically distinguished by reacting with a bidentate ligand. K instead for AgNO3 NO2 Cr minus, both are like same. That I think you can just practice it again. It will come even greater than C2, whatever the previous reaction we had. Again, CO NH3 4 CO3 on reaction with HBr give a green complex Y. Does reactant and product both show optical activity? CONH3 4CO3 and reactant with HBr give a green compound Y. Does reactant and product both show optical activity? So if we react with what it will form, it might form this CO4 Br2. Now this is a ligand of kind Ma4B2. Now Ma4B2, here only cis and trans isomer possible, but no optical isomer will form. That if we have read Ma4B2 kind of complex will not show optical isomerism. What kind of ligand will show the optical isomerism? We have this like to go into the detail, like somewhere MAB3 kind of like AB thrice kind of ligand where we have two formula delta and lambda that can be. So both will be optically innate. That is the like 12. The stability constant of NiEN3 is much higher than the NiNH3. 2. Both contain NiN1. This will happen because of NiN has perfect octahedron, whereas NiNH3 is a distorted octahedron. NiN has shown Chillet effect due to bidentate ligand of ethylene diamine. NiN distance in complex shorter than NiNH3 or NiNH in NH3 6 2 plus complex will show less after overweight with this. So what will be the correct? So the professor has told like if you have series of formation constant like K1, K2, K3, like Kn. Now we know that always Kn greater than um, like always uh, Kn will be less than by the Kn minus because once so the regular decrease in your stepwise formation constants is basically y because the increase in the charge density of metal ion by replacing on the equivalent by its more basic character of ligand and hence more electron donating tendency than water. So affinity of metal ions to our new ligand will decrease. And others is the steric factor. But this is not the always case where Kn will be less than Kn minus 1. So where Kn may greater than Kn minus 1, that is the question. So the question maybe it is in the change in geometry or change in the electronic state. So once sorry, so once we will go to the once we will read the crystal field theory, so we can see that if a low spin complex form after a ligand substitution over high spin, then that formation constant will be higher than the previous one. Or suppose somewhere chelation is forming or somewhere more stabilized geometry is forming, then your Kn will be greater than Kn minus 1. So our chelation is happening, that is giving in the less entropic uh, system. So in that case, your formation constant will be higher than the previous one. So basically here why Ni N3 will show because Ni N3 will show the chillet effect due to the bidentate nature of the ethylene diol. Now question is that complex of CuNH35 NO2Cl CuNH35 ONO are example. So here again, this is the NO2, this is ON. So this is basically your linkage isomer, where like linkage of the uh, ligand is different. So the next is total number of geometrical isomer of RCl, CO, PPH3, NH3H. Can anyone just tell? Yeah. So this is called MABCT. So what we can do, we can put M, we can hold A and just change the intersection BCT MACBT MA and then we have uh, CDP. So these are the three isomer possible geometrical isomer MABCT. Okay, the stability constant value of Cu NH34 and Cu NH122 respectively high. Then again, I told you the rate formation constant will be high once we have like something which stabilize the geometry in the forward direction. So here the chelation effect is there. That's why Cu En2 2 plus has higher formation constant because chelation will lead to a less entropic structure. The ionization isomer for this CrH2O4 BrNO2 BrH. So what is the answer? Can anyone tell? So ionization means it should give a different ion. So which ion should can change? If we change Br, No result. If we change Na to Br, that will be. So Cr H2O 4 Br 2 Na. This is your correct answer. So where is that? This is the answer. The formation constant for this, yeah, the formation constant of CuNH3 4 2 plus and CuH2O4 2 plus upon reacting with ammonia, the formation constant are K1, K3, K3, K4 are this respectively. The formation constant for CuNH3 2 plus. So what will be the formation constant? Can you tell the answer for this question? Can you tell me what will be the answer for this question? Or at least how, because I'm not going to solve this, but I can tell what is the way to solve this. So we can write Cu H2O4 2 plus 1 ammonia equals Cu H2O3 H2O3 and H3. Right, this is your K1. So K1 is nothing but Cu H2O3 NH3 divided by concentration of Cu H2O4 2 plus NH3. This is K1. Similarly, you have to write K2. K2 we have to write it like Cu NH3 2 H2O 2 divided by, then again we have this one Cu NH3 H2O 3 NH3. So this is the K for K2. Similarly, we have to write K3 and K4. Now, how we can form this Cu H2 NH3 2. So this will be how, like, we can get from Cu NH3 4 plus 1 water molecule. Okay, will give Cu NH3 3 H2O 4 H2O 1, right? 2 plus. So this will be the like required K will be Cu NH3 3 H2O 2 plus divide by, from where it will go, Cu NH3 4 2 plus into water. So how we can change and give, like what is the relation between K to function of K1, K2, K3, K4. So you have to find out the K in terms of K1, K2, K3, K4, and then finally you have to write the. So this is the where CuNH3 3H2. This is here, right? Where? Okay. It is in the somewhere K3. This will not tell. 1 minute. Let me just. Okay. Let me just take the eraser. not able to, I can insert one new slide. So we can write like, I will just write in detail. So we have Cu is 204 2 plus NH3 is giving Cu is 203 NH3 2 plus. This is your K1. So K1 is Cu is 203 NH3 2 plus divided by Cu is 204 into NH3. Similarly, you have to write up to K4 and find out the relation of K in terms of K1, K2, K3 and K4. So what is the relation? If you find out, then you will get the answer of this one. See, 7.4 into 10 to the power 10. Now we'll go to when a molecule is treated with AgNO3, 3 mole of AgCl are precipitate. Identify the structure of complex A. So we have 1 mole in the excess of 3 mole of AgCl is forming. Identify the structure of complex A. So 3 moles of AgCl is forming means 3Cl should be outside the coordination sphere. In ionization sphere, 3Cl should be minus. So this is the correct answer directly. Based on the given value, identify the complex ion which is most stable. So we have Kf for 8.0 into 10 power 2 minus log NiCN for Kd is minus 13.1. Kd it has given 2.2 in addition. So basically one which has highest Kf will give the okay. So one which have highest Kf value will be more stable. Now we have to find out which one is having the highest Kf value. Just okay. So this one has formation constant is 2 into 10 power minus 20 10 to 20 34. It has this log Kf is 13.3. So if you write Kf will be 10 to the power 30.3. This one will be the 10 to the power minus 31.3 Kd, and this one has 10 to the power minus 29. So obviously this is somewhere wrong, right? Based on given which is most chaos system. Okay. This is dissociation constant they have given. Okay, so formation constant will be the reverse. So correct option is C. So this is having 10 to the power minus 34. It's the highest. The isomerism shown by the CuNH3 4 PDCl4 and this one is what kind of isomerism is? So again, this is the coordination isomerism, because if you consider one is as a like a ionization sphere, other is the coordination sphere, so they have chain interchange like ClNH3. So coordination. So again, a cis trans isomers are chemically distinguished by just by reacting up identity. That is the correct answer for this. Ma'am, can you ask your question? What is your question? Hello. Ma'am, can you ask your question? What is your question? Okay, no question. I will just sign it.